Hey there, welcome. What we really want to do now in our series on building neural networks with APL is to implement the backpropagation algorithm, which is the algorithm that will enable our networks to learn. And we really want to do that, but in order to do that in a decent way, so in order to write some decent code, I need to show you what Tradfns are and how to use traditional control structures. So if you are familiar with Tradfns spelled like this, so tradfn and tradfns, and with control structures like a for loop in APL. Feel free to skip this video, otherwise I'll just show you how it works. Okay, and so by now you have seen that APL is this array-oriented language, right? So if I have a series of values, for example 10 integers, and if I want to add 1 to them, I don't need to use a loop, right? And this I'm doing this I'm saying this especially for those of you who have some programming experience with other more, let's say, traditional programming languages. So you would probably need to use a loop in order to be able to add 1 to all of the elements in my list. And so the fact that APL is array-oriented means that all of these things usually happen implicitly. But there are times where it really is complicated or messy to do things or to try to do things in an array-oriented way. For example, for our backpropagation algorithm, that recursive definition really is not so nice or not so pleasant to the eye to write with the APL primitives, and so I will show you another alternative, and then you can choose for yourself what you prefer. So for the forward pass, we used something with the power operator. That was one alternative. We could do something similar for the backpropagation, or we could do something similar to what I'm going to show you, and then it's up to you to decide what you prefer. So these traditional control structures, like the for loops, they can only be used, or let me put it the other way around. So they cannot be used inside diffns, and diffns are these functions that we have seen that are defined with curly braces. So these diffns, and diffn stands for dynamic function, are fairly recent when compared to APL as a language. And in the beginning, there was only one type of function, which is now called tradfn, for traditional function. So let me edit my tradfn. And tradfns are defined in a different way. So I like to include these two characters, these two del's, which you can type with APLG, if I'm not mistaken. Yes, exactly. So APLG types these two characters. And these are not strictly needed, but I like them for the aesthetic hint that this is a tradfn. And now the way you define a tradfn is the following. You type in the name of the return value. So let me say that the return value now is called out. And then you say that out gets. So it looks like you're assigning something, and then the right argument goes in here and you have to name it. So let's say that this is the right argument. And then you can also give it a left argument like that. And so what this is saying is that the out is going to get a value after you call the tradfn with the right argument right and the left argument left. And you can name these different things, of course. You can call these bananas. And then what you do here is say that our tradfn only sums things. So what you do is you take the output and you have to assign to it, because that's the way tradfns return. They will return the value that is inside this variable here. So you return whatever you get if you do left plus bananas. Now you can fix this, and you can go over here and you can do something like 3 tradfn 5, and now it's adding things up. Now there's something really well, I find annoying, but there's something slightly annoying with tradfns, which is by default temporary variables are not local. so temporary or auxiliary variables are not local. So if I do something like this, so there's the TMP for temporary. So I have this variable that I'll say it is the left plus the bananas, and then I'll say that the output is equal to that temp variable. Now if I fix this, and if I call the function again, notice that all of a sudden the variable TMP exists over here. In a way, it leaked to outside of the function, and at least for me this is a little bit annoying, because if I had some other variable, say, or if the variable had some other value like hello world, I define this, right? I'm using this, it's helpful. Now I call this function, so I do 3 plus 5, and now all of a sudden my variable changed its value. So in order to prevent this, we need to tell the Tradfn that this variable should be local. It should not leak to outside of the function. So let me restore the value of TMP, and the way you do that is in front of the function definition. So this is the signature of the function, because it tells me the name of the output and the arguments it takes. So in front of it, you type in a I think it's a semicolon, right? You type in a semicolon, which is the dot and the comma, and then the name of the variable that you want not to leak to outside of the function. Now what this says is, well, TMP is local. So now you can fix this again. So let's check. TMP is hello world. I'll do 3 plus 5, and now TMP is still hello world. And if there's if there's more than one, now the way you do that is you add another semicolon and the new name. So this localizes the names. And by the way, if you prefer, or if you have a long list, what you can do is you can do this on the second line. So you can do it like that if you prefer. So this localizes the names. So I can fix the function, I can do 3 plus 5, and now you can see that TMP2 doesn't exist. See, TMP2 undefined. So this is Tradfns in a nutshell. Now what's relevant, or what I wanted to show you, is the control structures, or I also wanted to show you that. So let's do the following. Let's close that Tradfn. Let me erase it because I don't want it to stay here. And now let's create a new one that is going to sum a vector of numbers. So in APL, the correct way to sum numbers, a vector, well, not the correct way, but the usual way in which you do it, and probably the preferable way, is to use a plus reduction. But just for the sake of demonstrating how a control structure works, let's do that in a Tradfn with a loop. So I like to add these as visual reminders that this is a Tradfn, but again, this is not necessary. And now let's say that the sum gets, so the function name, and now the argument. So let's say it's a vector of numbers. Now what I'm going to do is I'm going to, well, I can initialize the sum as 0, right? Because in the beginning I have added nothing. And now what I do is I type in a colon 4, and then this 4 is matched by an AND 4, much like a namespace, a colon namespace is matched by a colon AND namespace. Now 4, and now what I need is my iterator variable. So for, let's say, for number, and I type in colon in, and then on the right you insert the thing that you want to iterate over. So for number in vector, and this reads as like for each number in vector, or let number be each of the values in vector. And now we just write our regular code. Now the problem here is, notice that this is orange, whereas these two names are white, and that's because I need to localize the variable number. Now I can fix this, and I can type in sum 1, 2, 3, 4, 5, and I get 15. Okay, and so this is what is going on. This is adding things. Now let me also show you a second thing which is going to be helpful in the backpropagation algorithm, and that's when we want to iterate over a couple of things at the same time in parallel. So let's do this. Let's close this. Let's erase this because I don't want this. And let's create this function zip. Now what this function zip is going to do is, it is going to take two vectors, for example these, and it's going to return pairs of things. So it's going to do 1a, 2b, 3c, and 4d. Okay, so this is what we want our function to do. So how do we do that? Well, let's see. So zip is going to be our function that is going to return some pairs, and on the right it takes two vectors. Yeah. Now the cool thing is, because we already, or because we want these vectors to be two of them, we can actually unpack them directly. So we can say that this is the vector 1 and vector 2, and the Tradfn reads this as a single argument, but it unpacks it for us. So it's more or less the same as doing v1, v2 gets 1, 2, 3, ABC. Okay, so v1 and v2. So this is unpacking. And now what we do is, well, the pairs start off to be a vector of length 0, right? Actually, this is an empty vector. So the pairs are an empty vector, so something like this, or an empty string, or an empty character vector. And now what we do is, for something and for. Now what we would love to do is to go over v1 and v2 at the same time, right? We would love to traverse them in parallel, but we can actually do that. And the way we do that is we type in the names of the two iterator variables, and now instead of doing colon in, we do in each. And now what this is saying is, for a and b in each of v1 and v2, and I also like to parenthesize these two. Now what we do is, we take the pairs and we append the new pair. And so that's going to be the pairs, and then comma to catenate, and then the new pair, which is going to be AB. But now we want to catenate these two vectors, so this needs to be a scalar, so we need to enclose it. Now A and B are in orange because they need to be localized. So let's do that. And also, instead of doing this, sorry about that, I think I already told you this, we can just catenate. Now we can fix this, and now we can try to call zip in here. And you can see that it zipped things together. And so the essential things here are, or for you to learn about and to practice a little bit with, is the definition of Tradfns and these control structures with the for and the in each and etc. And then there's the for, and then there's other things like colon while, colon if, colon switch, not switch, select, and etc. But these should be used sparingly. So if you have programming experience with other languages, don't get crazy about this and don't start writing APL as if it were some other language. Because, for example, this zip operation, the way you could do it in APL would be, you would, gosh, why do I keep forgetting the name of this? Split. Yeah, you would split the transpose of the mix. Yeah, so it's exactly the same thing in APL. And so this is the APL code you should strive for. Notice that this is 3 glyphs versus 4 lines plus a header and a couple of localizations. Yep. So I hope you learned something new, and in the next video we will use this to implement finally the backpropagation algorithm. Bye.